So this is example 20.8 from the book, chapter 20. And the reason why I'm showing this example is to introduce a few terms that we haven't yet had a chance to discuss in the class. The main terms that I want to introduce here are null hypothesis and alternative hypothesis. So a null hypothesis versus an alternative hypothesis is essentially, a null hypothesis is if nothing changed, this would be true, this would be the case. So, if someone said the world is flat and your hypothesis is arguing that the world is round, the null hypothesis would be everything is the status quo, so the world is flat, so the null hypothesis would be true. However, if you were to somehow prove statistically that the world was round, which we know it is, you would actually be able to say that your alternative hypothesis that the world was round is true based on your statistical analysis. Now, of course, we know that the world is round, so that alternative hypothesis was true, but you can kind of understand what I'm saying here, hopefully. So this example talks about a null hypothesis, and their null hypothesis here is this top one, which says H sub 0, or the null hypothesis, mu, the mean, population mean, is equal to 0. The alternative hypothesis, should the null hypothesis be incorrect, is that mu, or the population mean, is greater than 0. So they give you some information here to help you kind of come to some of these conclusions. One is that the sample size is 25, so they've taken 25 observations. And it has a value of t equals 1.75. So they've given you the t value and they've given you the population. So let's write those things down. So n is equal to 25, which implies that the degrees of freedom is equal to n minus 1, which is equal to 25 minus 1, which is equal to 24. So you have 24 degrees of freedom. And we have this t value, which is equal to 1.75. So we've answered part A. What are the degrees of freedom for this statistic? So now part B asks you to give two critical values t from table C that bracket the t. So in other words, they want to know where t lies between. What two t star values does this actually lie between? And what are the one-sided p-values for these two entries? So to do this, we need to look at a t-table, and here I've put a t-table up, and I am looking for 24 degrees of freedom. So that's my first piece of information. So I can go to this degrees of freedom column, and I can look for 24, which happens to be right there. Now I can go across that column and look at each value in that row for 24 and look for something that's close to 1.75. So I know as I traverse through here, I'm going to get up to 1.7, and I'm probably going to stop because 1.7 is pretty close to 1.75. But it's smaller than 1.75. So the number after that here is 2.064. 2.064 is greater than 1.75. So now I know that this is the range. This is the range that my values are going to fall between. So now I'm also given that this is a one-sided p-value. So what that tells me is that I need to look at this top row here on the bottom, one-sided p. So if I take my range that I've already found, and I just sort of follow them down this table, I'll see that I get these two numbers here. So now I have the 1.711 and the 2.064 as my t-values, and then at the bottom my p-values are 0.05 and 0.025. So what that tells me, and again this is part A right here, part B, what it tells me is that p is between 0.025, it's greater than that, or it's greater than that, sorry, I wrote this incorrectly, It's greater than 0.025, but it's less than 0.05. So it's somewhere in between those two numbers. Okay, so this is part B. So part C asks us, is the value t equals 1.75 significant at the 10% level, at the 5% level, or at the 1% level? So let's look at each of these. So at the 10% level, we can translate that into 0.10 as 10%. Another way to write 10%. So P is between 0.025 and 0.05. So at the 10% level, P is actually less than 0.1. So P is less than 0.1, which means that this is significant. At the 5% level, that we can translate to 0.05. Well, this is a little deceiving because we have up here that z is less than 0.05, which implies that it doesn't include 0.05. It's less than 0.05. So P is actually greater than 0.05. Or 0.05 is greater than P, excuse me. So this is significant. So the last part of this question is it significant at the 1% level? So 1% we can rewrite as 0.01. And now 0.01, well, P is actually greater than P. So, or P is greater than 0.01. So this is not significant. So essentially, if the number is, if the p-value that we get, the closer to 0 it is, the less significant the number would be. So in this case, the closer or further away from p the p-value is, if it falls within the range, or p is less than that value, so in other words, the greater the number is from p, the more significant that number, that level will be. So part D asks, if you had some software and you could accurately calculate the exact one-sided p-value for t equals 1.75, how would you do it? So we could do this pretty easily, actually. We could, and I actually created a spreadsheet, and when I did that, I used Google Sheets, but I think this would probably work in any spreadsheet program, is I typed in equals in the cell, t.dist, and I typed in the t value, which was 1.75, the degrees of freedom, which is 24, and then true to indicate that I wanted a cumulative distribution of the numbers. And this should yield, I believe it's 0.9 and some change. But this isn't the true one-sided p-value for this, because if you recall, we're looking to find everything that's greater than 0. And our null hypothesis was everything that equals 0. And so we're actually looking for the difference between 1 and this number that we came up with. So if we subtract those two numbers from, or that number from 1, so 1 minus that 0. I actually forget what the actual value that I got was, but 0.9 whatever, we get something around 0.0464, I think, is the number. So this is the actual value that this lies in between. So you can see it's pretty close to 0.5, but not quite. 0.05, I should say, or 5%, but it's not quite. It's 4.6% is where it comes into play here. So it's between the 90th and the 95th percentile.